Now we know about the two different interpretations of probability, the frequentist, which is based on frequency, and Bayesian, which is more subjective. And we also said that even though there's no agreement on the interpretations, regardless of what interpretation approach you take, there will be certain axioms or probabilities that are going to follow for sure, regardless of what you choose. Okay, so to introduce you now to the axioms or probabilities, let me first talk a little bit about how everything came up. Okay, the foundations of modern probability theory, the axiomatic basis, laid by Andrew Kolmogorov in 1933. Okay, so he's a really famous and accomplished mathematician who also did a lot of work on probability. Okay, like I said, the axioms themselves, they're not concerned with the actual interpretation of probabilities. They're only meaning that probabilities are defined by a function satisfying these axioms. Okay, so even if you take, regardless of whether you take the frequentist or the Bayesian approach, they're all going to follow those axioms. Okay, so let's talk about those axioms. Okay, they're actually, if you read the book, you know that there are three main ones here. Okay, so we're going to start with the definition P, okay, to be the function. So again, earlier we're talking about P is a probability, and now we start to say that it is a function. Okay, and I guess no wonder, well, we usually write function like say P parentheses and whatever goes into it. So this actually, the notation itself probably already tell you to some degree that, well, P is actually a function. All right, so P, probability is a function, assigns a non-negative, okay, something to highlight, okay, real value to each event E of a sample space S. We will call P a probability if, okay, three axioms, like I said. First of all, it needs to be non-negative. Actually, also, it has to be bounded about by 1. Okay, so we know that probability is between 0 and 1. So, okay, not surprisingly, right? It cannot go below 0, but it could be 0. Okay, it is bounded about by 1. So it could go up to 1, but it won't go beyond 1. Okay, so non-negative and also bounded about by 1. That's the first axiom. The second axiom is that the total should be 1. Okay, so when we say total, we're talking about the sample space. So recall, we have defined sample space as all possible outcomes, right, of the experiment that you're working with. So if I consider all possible outcomes, which is the sample space, okay, so the probability of the sample space should be 1. Okay, so this means that in the sample space, something will happen, right? Like it could be like nothing happens in the sample, like let me put it this way, the sample space, if you remember the example, let's just say flipping a coin, let's just say tossing a die, right? And we know that the sample space there is what? 1, 2, 3, 4, 5, 6, okay? So what this tells us, like total 1, what this tells us is that if we flip a coin, flip a die, toss a die here, we know that it has to be one of them. Okay, so meaning that the sample space, like the probability of the sample space, like one of them going to happen is 1. Okay, so this maybe sounds trivial at this point, but later, which is actually now we go to the third axiom. Okay, so what we mean by countable addition is that you are able to actually, even though we know that the total is 1, but what's more important is that, well, in this example, it has to be one of the 6, right? It cannot happen at the same time, okay? And, but then it has to be one of the 6. So in addition to axiom 2, that we know that the total is 1, we also have this axiom 3 talking about countable addition. In this case, we're talking about like an infinite number of events. But one way to think about it, say like if we go back to this example, okay, tossing a die here, then we know that like for all of the 6 different outcomes, possible outcomes, EI, let's just say any EI and EJ, okay, they have no intersection because you cannot like toss a die and then get 1 and 2 at the same time. You can only get one of them. Okay, so this is what we mean, like they are disjoint, if you remember our terminology before. Okay, but also if you look at the union, okay, of all of the 6 possibilities out there and then do the probability, well, actually becomes the S, right? Because the union of all of the 6 different events is actually S itself. Okay, but here the axiom 3 is actually even more generic. Okay, And once we get to it, talking about infinite number of possibilities or possible outcomes, we'll see that this is going to apply again. Okay, but regardless, like I said, in the k disjoint events, like what we're talking about for tossing a die or like flipping a coin, tossing a die, then it's going to be k disjoint events that we're able to come up with. And then this axiom 3 actually reduces to this finite number of possible outcomes, okay, the events, okay? So the probability of the union of all of this will be the sum of each of the probability, okay? As an example, let's just say we come back to here, okay? Let's just say the left-hand side, like I want to know the probability that if I flip, if I toss a coin, I can get 1 or 2, okay? So like union, remember, is A or B, right? 1 or 2. So the left-hand side is I want to get A or B, 1 or 2. And based on this axiom 3, we know that, well, it is the same as summing up the probability of getting 1 and probability of getting 2. Okay, when that happens, well, if it's a fair die, we know that this is going to be 1/6 plus 1/6, which is going to give you 1/3. Okay, so again, right now we're mostly talking about the disjoint events, which is countable. Okay, we have a finite number of them. Okay, but later when we move to continuous cases, as you know before, like in the introduction lecture, that we're gonna start to bring infinite number of events out there, and then the still regardless, the axiom 3 gonna hold there.